Hello, my name is Kylie Bain, and this is my lab report for phys2212lab4, microscopic view of DC and RC circuits. So for the contents of this video, we'll go through the introduction and then the charge and energy conservation in series. The prediction of what the current will be, we'll replace the ammeter with voltmeter, look at the potential differences in each section and graph them, and then talk about findings. Then we'll go to the second part of the lab, which is RC circuit observation and results, and then time-dependent voltage, find the value of RC and graph those over time, and finish with the what-if questions. So to introduce the lab, the purpose was to use energy and current conservation principles to predict and perform experiments to model behavior of circuits in parallel and series, and to measure values of conventional current and potential differences, as well as analyze the behavior of resistors and capacitors. And the results for part 1 are listed there, but we'll talk about those later. In part 2, we found out that when resistance is greater, the capacitors take longer to charge. So first I made a circuit in series with two 1.5 volt batteries, 2 resistors, and 2 ammeters, and predicted the currents in current 1 and current 2 to be 0.02 amps. And then using the website, we found out that that was correct. Then when the ammeter was read backwards, it was also 0.02 amps. And when I replaced the ammeter with a voltmeter, the new numbers for the voltmeter was 3.0 volts and the ammeter was 0 amps. Then I removed the voltmeter and closed the circuit with a wire, and used the voltmeter to measure potential differences across each part of the circuit, and those are listed below. And then I found out that the round-trip potential difference was 0, as it should be. This is my graph to approximate potential versus position. You can see that it charges from 0 to 3 volts when going through the batteries, and then loses the voltage as it passes through the resistors. So I can use R equals delta V over I to calculate the resistance of each element of the circuit. So the 47 ohm resistor was 47.95 ohms, and that's because of a rounding error with the 0.02 amps. The 100 ohm resistor was 102.05 ohms, and the wire and the ammeter were both 0. So then I created a circuit with a 10 and 20 ohm bulb and a 9 volt battery and a 200 mF capacitor. So I connected the battery and capacitor in series and observed that the light began to dim over time and eventually went out. And then the exact same thing happened when I disconnected the battery and connected the capacitor to the 10 ohm bulb. Then when first connected to the battery, connecting the battery to the capacitor and the bulb, the capacitor was charging and the current slowed down. And then the current slowed down again when we removed the battery. Here are pictures of the capacitor charging. Alright, then in the RC circuit, the recorded time for the charge of the 10 ohm bulb was 19.8 seconds, and the discharge of the 10 ohm bulb was 20 seconds about. Repeating it with the 20 ohm bulb, 39.36 seconds and 39.42 seconds to discharge. So the result of that tells us that the capacitor takes longer to charge when the resistance is greater, as I said before. Then the time-dependent voltage across a discharging capacitor, we can use the QC minus IR equals 0 equation to create a differential equation of Q over RC plus dQ dt equals 0, and then basically solve for the time constant RC as seen in the last step. So after plotting natural log of delta V over delta V naught, we get a straight line with a slope of -1 over RC, where RC is the time constant of the circuit. Then I solved and got RC equals 6.0096 about, and comparing the voltage at the time constant value compared to the initial potential difference multiplied by 1 over E, the error was 0.03%, which is pretty good. These are my graphs for natural log of delta V over delta V naught versus time and voltage versus time. And then the what-if questions are, if we were doing this lab in real life, the resistance in a real ammeter would not equal to exactly 0, because in order to calculate the current flowing through the circuit, they need resistance. And then the second question is, and if you used a real-life battery to charge a real capacitor, so the model predicts the capacitor to reach full charge more quickly than in reality because the batteries lose charge over time.